All right. Once you have the displacement x as a function of time, we can easily get velocity and acceleration as a functions of time. For velocity, what you do, you take time derivative with respect to x. The cosine function becomes a negative sine function. And for acceleration, you take one more derivative and you get negative omega squared times a cosine omega t plus delta. Sine goes back to cosine. Now the interesting thing is, this part, as you recall, is just the displacement x itself. And that shouldn't come as a surprise, because the reason why a is proportional to x is because, after all, a is proportional to f, right? F equals ma. So you see, f equals ma. If I multiply both sides by m, then I have f equals ma, and that is, this side becomes negative m omega squared x. Now, omega squared is k over m, isn't it? And therefore, m omega squared is simply equal to k. So this is basically saying f equals kx, which is exactly what we're looking for. Now, having studied the simple harmonic oscillation with Newton's second law to find its displacement, velocity, and acceleration, we can take an alternate approach. Let us look at the energy aspect of the simple harmonic oscillator. If you have a mass attached to a spring with a spring constant k, then if you ignore the mass of the spring itself, just look at the mass of the object attached to the spring, mass m, and then you find that as far as the mechanical energy of the system is concerned, there are two terms. The mechanical energy E equals the sum of the kinetic energy of the mass attached to the spring plus the potential energy of the spring itself. That is the elastic potential energy. And since the only force doing work for the mass spring system is the elastic restoring force of the spring, and that force, as we learned in Physics 1A, is conservative. Okay, if all the forces doing work are conservative, then of course the system must conserve mechanical energy, which means when you add these two terms up, you should get a constant. Is that right? Well, we don't have to take this for granted. We can actually plug in the value of v and x into it to see if it works. Okay, take a look at v. V is a sine function, so itself varies as a function of time. X is a cosine function, that's x. Okay, both terms change as time changes. But when you add them up, what happens? Okay, let's take a look. The first term, negative 1/2 m. Here is v right here, I have to square it. Omega squared, a squared, and then sine squared, right? Blah, blah, blah. The next term, 1/2 k x squared. X is right here, so we have to square it as a squared, cosine squared, whatever, whatever. Now, you have a sine squared here, you have a cosine squared here. Of course, if you add them up, you get 1, which is perfect, which is independent of time. But of course, the condition here is that this prefactor must equal to that prefactor. I take them out, then I can combine the sine squared and cosine squared. Are they equal to each other? Well, we better hope they are. Well, in fact, unfortunately, that is the case. The first term is 1/2 m omega squared a squared. The second term is 1/2 k a squared. So the difference here is m omega squared, and the next term is k. But as we learned, m omega squared equals k. So therefore, indeed, they're equal. I can take them out. I can write either the first expression or the second expression. Why don't I write 1/2 kx squared? Okay. Then what's left is this sine squared omega t plus delta plus cosine squared of the same argument. Of course, that equals 1. So the answer is 1/2 k a squared. And indeed, you learned that energy is conserved. As a matter of fact, we can even go we can even proceed this way. Instead of using Newton's second law to solve for the differential equation of motion, this and that, all we did, we can even start with this first. We simply write down the energy of the simple harmonic oscillator, which is the block and the spring system, and then we say here, okay, this is the v here, this is the x here, potential energy and kinetic energy. right? Now we don't know what omega is, but we do know one thing, and that is when you add these two terms up, you gotta have a constant. This is sine squared, this is cosine squared. They both depend on time, but if I add them together, they become time independent, which is equal to 1. But the condition is these two prefactors must be equal to each other. If they're not equal to each other, you cannot combine the sine squared with cosine squared, and E would depend on time, which violates conservation of energy. So you see, the conservation of energy also requires that m omega squared be equal to k. And in fact, with that, I don't have to go through Newton's second law approach. I can simply use conservation of energy to determine what omega is, and I can also find what that total energy is equal to 1/2 Ka squared. Now, take a good look at 1/2 Ka squared. What is A? A is the maximum value of x, isn't it? And therefore, 1/2 Ka squared is just the maximum value of 1/2 Kx squared, which means it is the maximum value of the potential energy of the system. So why is it that the maximum potential energy also equals to the total energy? Well, we have to understand when x reaches a maximum. When x reaches a maximum, you're either at full compression or full stretch, right? That's when x equals positive or negative A. When the potential energy is, of course, a maximum. Is the block moving? No, it's not at that moment. And therefore, you have this term, the potential energy term, which reaches the maximum, and you have the kinetic energy term, which is 0. Of course, when the kinetic energy term is 0, all energy is potential. That's when potential energy is a maximum. So indeed, the total energy equals to the maximum amount of potential energy. And similarly, we can argue that it is also equal to the maximum amount of kinetic energy, because it is also possible for x to be 0. And when does that happen? That's when the object passes equilibrium position, right? It zips past equilibrium position. So the potential energy is 0 because the spring is neither compressed nor stretched. Now tell me, at this particular moment, is the kinetic energy also 0, which means once it reaches the equilibrium position, is it stopped? Of course not. According to conservation of energy, it is not the case. In fact, not only is it not stopped, V has to be the greatest because the second term is 0. Please do not confuse 0 acceleration with 0 speed. It is true that when the object passes through the equilibrium position, its acceleration is 0 because the force is 0. Okay, force negative kx, x equal to 0. Now, 0 acceleration, does that mean 0 speed? No, it means maximum or minimum speed. That's what it means. In this case, it is maximum speed. Okay, so what is that maximum speed equal to? Well, let's see. From conservation of energy, what do we think the maximum speed should be? Well, we make E, which is equal to 1/2 mv maximum squared, right? There's no potential energy when passed through equilibrium. But we know it is also equal to 1/2 Ka squared, as we learned before. This tells us what V maximum is. Equals to this A times the square root of K over M. And that, as you know, is omega times A. That is the maximum speed from conservation of energy. Does that agree with a direct calculation with V equals dx dt? Well, let's see. Let's put in the previous slide. You see here, this is the speed at any time. It's a function of time. You see, negative omega A sine omega t plus delta. Now, we're looking for the maximum value of V. That happens when the sine function becomes maximum, right? Plus or minus 1. So what is the absolute value of the greatest speed? That's when you take the sine function and let it equal to 1. Don't worry about the negative sign because I'm looking for the magnitude. So what's the answer? Omega times A. So indeed, this is correct. Whether you use conservation of energy or use dx dt directly to find the speed, the maximum speed is always equal to omega times A. Okay, another interesting thing I want to talk about is the relationship between simple harmonic motion in one dimension and uniform circular motion in two dimensions, which you've studied before in 1A. We learned before that omega stood for angular velocity or angular speed before, but we use the same symbol for angular frequency. And so, there is some sort of connection already between rotation or circular motion and simple harmonic motion. But there is, in fact, a very explicit connection between the two. Imagine a two-dimensional circle, x and y, in the xy plane. An object starts from a certain distance, from a certain point here, and moves at a constant speed in a circle of radius a centered at the origin. The vector, which tells us where the object is, we call it vector a. This vector a makes an angle of omega t plus delta from the x-axis. What does that mean? It means that at t equal to 0, the vector is right here, and that angle is delta. And it also means that as the object moves, it moves at an angular speed of omega. Therefore, the actual angle it covers over time t is omega times t, so making the total angle omega t plus delta. So at time t, the angle it makes with the x-axis is omega t plus delta, and therefore, if I take this vector, okay, and I project it onto the t-axis, what do I get? I get a times cosine omega t plus delta. Isn't this the simple harmonic motion we just discovered? So you see, there indeed is a very interesting connection between simple harmonic motion and uniform circular motion. Basically, you can take an object doing uniform circular motion, okay, in 2 dimensions, and you project this object. Imagine this object moves like this, right? At constant speed, right? And you project its shadow on the x-axis. As the object turns around, its shadow goes back and forth on the x-axis. The object does uniform circular motion, and its shadow on the x-axis executes nothing else but simple harmonic oscillation. Okay, now let's take a look at another important example of simple harmonic oscillation, and that's the simple pendulum. What's a pendulum? Well, basically you have an object dangling from the ceiling, and then you just pull the object to one side, let go of it, it starts oscillating. That will be a pendulum. What's a simple pendulum? Well, it's the simplest kind, which consists of massless string and a point mass attached to the very end of the pendulum. So it's a mathematical simplification, really. We can basically ignore the string's mass and ignore the size of the object, the bob, attached to the end. Now suppose I pull the bob to one side so that the string makes an angle theta with the vertical line, and I let go of it. Then gravity will try to pull it down so the thing starts to move this way and it starts to oscillate back and forth. That's called a simple pendulum. Let us try to analyze the motion of the simple pendulum. From Newton's second law point of view, there are 2 forces exerted on it. One is mg going down, the other is a tension pulling towards the center of the circle. Are these 2 forces balanced? Not really. Let us decompose the motion into 2 directions, which is radial, or along the string, and tangential, which is perpendicular to the string. Basically, the pendulum is doing circular motion, and this is tangential, this is radial. I'm not quite interested in a radial motion, because the radial motion, all it requires is that there is a tension which varies in magnitude so that to support the centripetal force. I'm more interested in the tangential motion. I want to see how the angle theta changes. The oscillation back and forth, which means theta can be positive and negative, and then the speed at which theta changes can vary. So I'm more interested in the angle theta, how it depends on time. So let us look at the motion along this direction. The net force along this direction, which is the x direction, sigma fx. What is that equal to? Well, as you pull the string this way, theta increases. And x really is just this arc length from here to there. So this direction is the direction of increasing theta, or increasing x. The net force along this direction is a component of mg, because tension is perpendicular to it. and that component is mg sine theta. And it is negative because it points that way, not towards the increasing direction of x. So the net force along the x direction is negative mg sine theta. What is it equal to? Well, according to Newton's second law, mass times acceleration in x direction, so m times second derivative of x with respect to time. Okay, there are two variables, theta and x. I don't like both of them at the same time, so I'm going to get rid of one. You know, x by definition, its arc length and the angle theta by definition, they're related. X over L equals theta. That's the definition of theta. So x equals L theta. I can either eliminate x or theta. Let's try to eliminate x. So x equals L times theta, which I plug in here. Replace x with L theta. Cancel that m and move the L to the other side. And this is what I come up with. Negative g over L sine theta equals the second derivative of theta with respect to time. Before we move on a little further, let's ask, what happened to the mass m? How come it just disappeared? We know it cancels out, right? Is this a surprise? Well, it shouldn't be, because you have to understand that this pendulum is powered only by gravity. Without gravity, the pendulum is not going to move at all. Anything that's powered by gravity only satisfies this unique thing, and that is the motion of that object is independent of its mass. That is only true when the thing is powered only by gravity, because gravity, unlike any other force, as you learned, its magnitude automatically increases as the mass of the object increases. So when you double the mass, you also double the force, leaving the acceleration the same. So there is no mass in this question, in this equation. That's one thing. Another thing is, how does one solve this problem? You know, this is also a differential equation, right? And looks innocent enough. It doesn't look very complicated to us because there's only sine theta involved. How does that compare with the equation that we solved before? Well, for mass and spring system, I can write something similar, except that side was this, actually the mass, and move the mass over there. What do we have here? Negative k over m, right? And x, that's the force. Now, if you compare these two expressions, you find that you can replace k over m with g over l. Negative sign stays. And replace x with theta. But there's one subtle difference, and that is there is x, but this side is not just theta, but rather sine theta. How does that affect the motion? How does it affect our solution? Well, it turns out that you might think this sine theta shouldn't bother you that much. You can still try to solve it. You know how we solved that problem? We guessed, right? We guessed, x might be a sine and cosine function. Now, try whatever guess you can come up with. See if you can solve it. Or better yet, let me tell you, don't even bother, because you cannot find the solution. Or more precisely speaking, you cannot find a solution in any elementary form that you have studied so far. Sine, cosine, exponential, tangent, arctangent, whatever you think of. Because the solution to this equation with sine theta, not theta, does not exist in elementary form. It's nothing that we learned before. If you really want to know it, it is called the complete elliptical integral of the first kind. Whatever the heck that is. For example, if you think theta is a sine function of time, doesn't that give you sine and sine of sine? And the other side is just sine, not sine of sine, right? So it's not something that you want to deal with directly. So what do? Well, this calls for some simplification, right? See, we don't like that sine function. We just want theta itself. We don't want sine theta. Can we replace sine theta with theta? Can we? But it turns out, yes, we can, if the angle theta is very small, right? So, if the absolute value of theta is far less than 1, okay, then sine theta is roughly equal to theta. Okay, So what that means is if we want to have a chance to solve this differential equation, we want to make sure that we pull the string only slightly instead of a very large angle. If we do that, we can safely replace sine theta with theta, and then we know how the solution should go, because these two becomes exactly analogous, because I can cross out that sine function, right? Just leaving theta. Therefore, simply replace x with theta, k over m with g over l, and here is our solution right there. Instead of x equals a cosine omega t plus delta, we know that I replace it with theta equals a, that's the amplitude. Here is theta maximum, the maximum angle theta, okay? Cosine omega t plus delta. Now, what's the value of omega here? It was equal to square root of k over m, and we replace with g over l. There we go. That's our solution to the simple pendulum. Omega is the angular frequency of the oscillation of the simple pendulum, and it's equal to the square root of g over l. Now that qualitatively makes sense, because a large g means the moment you pull the pendulum off balance, it's going to try to get down very quickly because gravity pulls it down very quickly. So you're going to have a large speed in oscillation, which means omega is very high, which means it goes back and forth very quickly. What about a large L? A large L means it's a very long spring, and that of course takes longer time to complete its motion. I don't know if you have been to the Griffith Park Observatory. In their rotunda, there is a huge pendulum, like 2 or 3 stories tall. It's called the Foucault pendulum. It was there to demonstrate the existence of the rotation of the Earth. The Foucault pendulum is being very, very long. You know, the time it takes for the thing to swing back and forth once is not a few seconds. It could be over a minute because of a very large value of L. You can easily test it for yourself. The greater the L value, the longer it takes for the thing to go back and forth. Now, T, the period of the oscillation explicitly is 2 pi over omega, so that's 2 pi times square root of L over G. Longer string means longer period. That is the simple pendulum.